Hello, everyone, and welcome to We Meet at Digital Days. My name is Lisa Richter, and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is Power Inductors, More Than Meets the Eye. Details of power inductor, key parameters, and design in various power topologies, and how RedExpert optimizes the selection. Our speaker is Mohamed Al-Alami. He will hold a presentation and will answer your questions. Before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentation. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all of your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all of your questions promptly. At the end of the webinar, you'll be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. You will receive the link to the presentation in the next few days. The recording will be available at our website shortly. So now I will hand over to our speaker, and I wish you a nice presentation.
Good afternoon, everyone. I hope you're all well and safe and ready to talk inductors. So for today, we will be looking at power inductors and looking into a bit more detail onto the selection of the components and the various different topics that we've looked at earlier. The first part of the agenda we look at is switch mode power topologies, and the idea behind this is looking at the various different parameters that would be key when it comes to selecting a suitable inductor, which we will cover in the second section of the seminar. So the idea behind this is to give you something that's outside the norm, not something that is very simple or basic, to maybe take it to the next level. I know I've only got 30 minutes, that's why I'm talking very quick. But we will try to look into something that would hopefully be a more value add and a bit more advanced in terms of the selection of these parts. And we'll try to see if we have got the time to present for you RedExpert, which is our flagship component selection and also design tool for power topologies, and how that can help you know and to select a suitable inductor. Let's look at the challenges first, and then we'll see, hopefully, if we have time, how the tool will help us. So with switch mode power converter topologies, we start off, and I'll just explain the two basic ones, the buck and the boost. The buck very simply, of course, steps down the input voltage. The topology, I think everybody's familiar with that. It's a very simple circuit. So the inductor and the capacitor, the filter components, sit on the output side. So during the transition on time, so your inductor current is energized, is increasing. During the off time, it's reducing, and that ripple current flows through the capacitor, and the average goes through to the output. And the following few slides are just showing a representation of some of these waveforms, and we're going to concentrate on, in this presentation, on the inductor ripple current. In the next one after this one, we'll talk about the capacitor side of things, but for now, let's talk about this delta IL, which is the change in ripple current, as a function of a few parameters, which we will come to over the next few slides, but it is the key parameter when it comes to selecting the inductor. It is in a way also your degree of freedom. This is your flexibility to select a value for this ripple, and we will see this in a bit. Why is this so important? It impacts something called CCM or DCM, operating in continuous or discontinuous conduction mode. It affects your output ripple voltage, as we will see more clearly in the next presentation when we start investigating that. Core loss and inductor loss in general. And of course, last but not least, our favorite, EMI emissions. So this selection of this particular parameter can have consequences for all of these different aspects of design. The ripple current can also be rewritten, and this is just maths. There's nothing specific here or special here. Rewritten as a factor, as a percentage number. The delta I divided by the average current flowing through the inductor is defined as the ripple current. So please just keep this value in the back of the mind. You will see it being presented on the next few slides, and I'll explain why this is something that we have done. On the next slide, we will see the first parameter that impacts ripple. So the ripple or ripple factor, delta I or R, is impacted naturally by the switching frequency of your converter. And you can play with that delta I quite nicely. If you increase the switching frequency, you drop delta I. If you reduce it, it becomes bigger. Now, the smaller, the better in terms of ripple current from an EMI point of view, from a noise point of view, saturation, all sorts of aspects. What's another important parameter that can impact on my ripple current? It can be impacted by the value of the inductance of the inductor that we use. So that value of L, if I use a large value of L, then the ripple is nice and small. So that's another method of trying to reduce the ripple, and vice versa, of course. You will see here we have rewritten the inductance equation as a function of that ripple factor of basically delta I, if you want to think about it that way. And the reason why we've done this is because this is what you will see in RedExpert, the selection tool I mentioned, available on our website, to allow you to select the inductance, the suitable inductance value as per your design parameters for your buck, your boost, your septic, whichever converter that you are using. So that's the advantage of writing this as a percentage as opposed to a raw value. So you can say, I want 20% ripple, I want 50% ripple. So that's that side of it. Another important point as well to mention is when you are also doing the calculation for this inductance, it's important to take into account the impact of the drop across the diode, across the switch, across the IRDC in the inductor, albeit that's not, shouldn't be a huge impact. The main ones come from the diode and the switch, but predominantly the diode, in terms of how it impacts your duty cycle, because that will also have an impact on the inductance you need to achieve a certain amount of ripple. And the bigger these values here are, VD or V switch, the bigger the inductance needs to be in order to achieve 20% ripple, say, or 40% ripple. You said, I don't want any more ripple than this. So that's where the impact can be. And it's important to take this into account. You will see that RedExpert, we do take the VD into account. It is the main parameter, to be honest, when it comes to L. I've just put in a summary here on this slide for your information on the various different parameter equations that we've just talked about. What I've also done, sorry, I beg your pardon. I've also included what I called L critical, which is the inductance at the boundary between continuous and discontinuous conduction mode. So this is the calculation for you, should you want to also use that as part and parcel of your decision making. We'll do exactly the same as what we've done with the buck. We'll do it also with the boost. And again, the boost is slightly different in that the inductor now is on the input side of the circuit. So the methodology of operation is slightly different. The waveforms are pretty much identical. The only difference with this to point out is that the average current in that inductor is the input current now. And the input current is very important because it's bigger, higher than the output current. Naturally, this is a boost, so it's boosting the voltage and dropping the current. The power is the same. Well, you'd hope it's the same on a good day. So that's the ripple current here, and it's ripple voltage. And the same impacts as what we've mentioned for the buck also apply for the boost. There's no difference there. Guess what? We have also got our ripple factor for the boost as well. What's the difference here? The difference is that the IL average is not I out as it was for the buck. Here it's I in. That's the difference. And accordingly, the inductance equation will be also different to account for that variation input as opposed to output current. The same impact and the same relationship between inductance value and ripple factor still exists naturally. No difference there. And again, one more time, take into consideration, and I've included the equation here to calculate the inductance based on the duty cycle where you have got a voltage drop across the diode, the switch, and the IRDC of the inductor. The summary of the equation is also included in here. And again, one last time, I've also included the equation for the boundary condition, L critical, between continuous and discontinuous conduction. Now, before we move on to the next section, again, the idea behind this is selecting the suitable inductor. That's why it's more than meets the eye. We want to see what is special. So far, we hopefully have got a generic overview of the various equations dictating the key values, parameters of currents, voltages through or across the inductor. What's important? Ripple factor, same thing. Now, let's have a look at how we can select an inductor. Before I do this, just to give you maybe down to the bare bones, the mechanics, the mechanicals, the electricals of how we actually construct and build an inductor. So inductance as a value is dependent on the material that we use, the cross-sectional area, the length of magnetic path length, that the magnetic flux lines flow through. That gives me the inductance value, of course, as well as the number of turns. The reason why I've also put this picture is to identify this issue of no air gap and an air gap. We will talk about this in a couple of slides' time, but the air gap or the existence of a large air gap, as you can see here, or no air gap because the flux lines are just flowing through the material with this component here, has got an impact on the inductance value. It also has an impact on something called saturation. So this is design. This is, in a way, what we do at Würth when we're thinking about introducing a new product. We look at all sorts of aspects associated with material, with wire, with air gaps, etc., etc. But this is just to give you an idea, is one size is does not usually fit all. And there is a difference between these components in terms of their behavior, and the devil's in the detail, as we will see in a little bit. Selection parameters. How do I select an inductor? I look into the data sheet and I see all sorts of parameters on. I see inductance value, okay, fairly simple and basic and straightforward. That's what you're going to select based on naturally when you've done the calculation. Rated current. What would rated current be indicative of? Rated current would be indicative of the average current flowing through my inductor. As defined in our data sheets, it's the current that results in a certain temperature rise, in this case 40 degrees in the part, so self-heating as we call it. Saturation current. Saturation current is the current that results in a certain inductance drop in inductance value, or drop in inductance value at that particular current. Could be 10%, it could be 20%, 30%. And we've got RDC, voltage rating, resonant frequency, a whole plethora of other key characteristics and curves and parameters that I think most people potentially know about or appreciate. They're very easy to use and make the selection based on. So what is missing? What is so special about what we're looking at today? What's different? There are important features to consider. So one of these features I mentioned or alluded to before when I talked about the air gap side of things. We call it shielded, semi-shielded, or unshielded. So if you've got a small or no air gap at all, you have got a much better EMI performance than an unshielded with a huge air gap like the part that we saw earlier. So this is a small air gap. it has got a less radiated EMI out of this air gap. The lesser number of turns needed to achieve the inductance means lower RDC. So you could say, oh, this is more efficient. So why do we then bother about making a big air gap inductor like this? The idea behind the bigger air gap, albeit it's not particularly great from an EMI point of view, it gives me higher saturation currents. There's also another advantage, less dependence of inductance on core material. So you tend to find these have got a tighter tolerance than the ones with a smaller or no air gap whatsoever. I'm still not happy. I'm still seeing there's something missing. So I don't think this is something that is necessarily, you know, the be all and end all. It's very important naturally, but this is not the end of the story. This is where I'm going with today's seminar. I'm going towards efficiency and losses. And this is where we see RedExpert plugs a huge gap in when it comes to selecting a suitable inductor. Why does it do so? Why is it important? Because this information is really difficult to find. Or is it? We'll see. So first of all, just a starting point, efficiency is very important. It's the talk of the day. Being green and efficient is something that is very key and important to all of us, down from our electronics to the way we generate electricity. So we don't want things that are big and bulky, that require fan cooling, that require heat sinking. We want something that is nice and small and cool. So what's the problem? No, we can easily find this information out. It's called I squared RDC. You said you've got RDC. You showed us how to calculate I. Just square that and multiply it by RDC. But then that's why it's not as simple as that. You are only taking a fraction of the story if you're doing just the I squared RDC DC losses. Core loss and copper loss have got more than meets the eye. Core loss has got, of course, the hysteresis and the eddy current losses. These make up a considerable chunk of the inductor or transformer, magnetics in general losses. Anything that you've got high switching voltages and currents through, you will have more core loss. Plus, we've missed a big chunk of copper loss, which is the AC copper loss associated with skin and proximity effect, especially in today's environment where we are switching at higher frequencies, where we are throughputing considerably higher power. AC copper losses become the more prevalent in some occasions even than core loss at some points in time. So over the next few slides, I'll discuss these in a bit more detail. I'll start off with copper loss. These are fairly straightforward. I squared RDC, like I mentioned, and this is just the DC resistance rho L over A of a copper wire. Naturally, when you use flat wire, you end up with a lower RDC than you have with a round wire. The reason being is the cross-sectional area of the flat wire is bigger. So you get a lower RDC, basically. It fills the window area better than you would with a round wire. So RDC for a flat is better. Now let's look at the AC copper loss. So this is in the wire, but the AC loss, not the DC loss. And this is associated with the eddy current losses. So the concept of eddy currents is if you've got an AC current flowing through the wire, that AC current will internal to the wire, not external, we know the external one, but internal to the wire generate a time varying flux naturally, ND phi by dt. And that internal flux will internally also generate eddy currents or induced currents within that wire. These currents will work against the flow of the intended current through the wire, through the center, physically the center of the copper wire, and support it on the outside. What that means is that you will end up with a cross-sectional area of the wire, copper wire, with very little current density through the center and most of it on the outside. In other words, that AC current is predominantly being carried on the skin, on the outside area of the actual copper. So all of this cross-sectional area is meaningless. It's only this slither at the output, let's just say, exaggerating, that you're going to be carrying current through. And this is best described through this example. This is called the skin effect, or the skin depth. And that skin depth is, of course, becomes narrower and narrower and smaller as you increase frequency, inversely proportional, as per the equation that we can see in front of us. So the higher the switching frequency, the smaller the area that carries that switching current, the higher the resistance, and the bigger the losses that you're getting through the wire. So this tends to be quite a substantial effect. Another one to keep in the back of the mind, flat wire is considerably better than round wire. We've got a nice little example here. Both of them have got the same cross-sectional area. So it's the same A. But the flat wire has got twice the surface area. So it's got basically half the resistance, the AC resistance, than you would get for a round wire. Hence why it's more efficient to do it like that. The other effect is the proximity effect, which is something that we've learned about in school in the old days. So you've got two wires carrying current. There will be a force between those two wires, and the field from one wire will impact the field in the other wire and reduce accordingly, further erode, I should say, accordingly, the current density being carried through the adjacent wire. So this is a mutual impact. So this wire will affect this one and vice versa. Depending on the direction of current, that reduction or impact on current density could be in the center, in between, or on the outside. But I don't care. It just means to me that my wire has got more resistance to AC now. It's got less current density. It's not allowing current to flow through. It's more resistive. So that's AC copper loss. So you can see there's a lot more than I squared RDC. And if we look at the core loss, which is the other side of things, the core material that we use, a lot of, and I've used this myself in years gone by, designed inductors and transformers based on the curves that you see in here in order to calculate or roughly estimate core loss. We could never do anything about AC copper loss. We could calculate I squared RDC, and the next step was to estimate core loss, and this would sort of guide us towards what we would be expecting in terms of losses in the transformer on the inductor. And what you see in here is the estimation of core loss based on graphs from various different core manufacturers use Steinmetz's equation based on sinusoidal excitation of that core material, usually a ring core, to estimate these curves and give you, based on the volume of the core material itself, and the sort of peak flux density as well as switching frequency, a certain amount of power dissipated in that part. But there is a huge level of inaccuracy and lack of representation, if I may call it that, of what actually happens in a DC-DC regulator. And this is where the missing link comes in the form of RedExpert. I'm not sure how much the audience knows about RedExpert, but to be honest with you, if I'm going to spend talking about RedExpert, I'll probably need a couple of hours, 2 sessions, just to talk about RedExpert and its full capabilities. But today, I'm just giving a very brief demonstration of the tool. It's a free tool. It's available online. You don't need to download this. You can just very simply go on our website, click the link for RedExpert, which is provided in this presentation, and you'll be able to start playing. And the module that we will be looking at today is the power magnetics or power inductors module, beg your pardon. And in there we will, I'm going to leave these presentation slides, I should say, for you to have a look through. I'm not presenting the tool using slides. I'll go online now and I'll show you the tool. But these slides just give you a brief background on the capabilities and why we think RedExpert is such a wonderful tool. In particular, of course, for inductor selection, which is the topic of our presentation today, using various different converter topologies, RedExpert is capable of calculating a very accurate power loss in the power inductor based on your spec requirements. So you enter your input voltage, your output power, load current, you specify the ripple that you want in the inductor, and RedExpert will return a group of components and it will show you the DC loss, the AC loss, the total loss, and guess what? Also, it will show you the temperature rise in the part. This is not based on any sort of particular model or equation like in Steinmetz. This is actually based on testing these product series on a board to characterize the behavior of a series of inductors under variable frequency, variable duty cycle, and variable power current going through. And accordingly create a model to describe that particular series of inductance which sits in the background in RedExpert and does all of the number crunching for you to calculate the overall losses in the component. This, as you can see, is based on square wave, rectangular wave excitation, which is the more representative of a DC-DC as opposed to sinusoidal excitation of a core. And of course takes into account duty cycle variation, where you see there's a huge amount of efficiency and accuracy when it comes to looking at duty cycle variation compared to the standard Steinmetz model, which tends to be quite accurate, but only around the 50% duty cycle. So without further ado, I'm going to jump across onto RedExpert to just show you a few examples of how we can do this. What I have also done is I have, and I'm not going to go through these at this point in time, I don't believe that we will have the time to do so. I have included a couple of examples here of something that you may find also quite interesting, and some links across to some of the potential selections for these parts. And this is just something to help you appreciate maybe taking the tool even beyond the standard its standard capability. So without any further delay, I'll take you across to RedExpert. I hope everybody can see this clearly. So this is the RedExpert Power Inductors module. So when you get into RedExpert, you can select one of our various different modules for our different product ranges. Under Power Products, the first link takes you to the submodule for Power Inductors, which is where I am here. So you can see we have got 2,681 inductors available to select from in our product portfolio. There is loads of fantastic functionality for RedExpert, allows you to add components into a basket. You can select up to 16 parts and put these parts down here. You can compare their characteristics down at the bottom here. But this is what I was, I guess, alluding to earlier. If I wanted to explain RedExpert's key functions and capabilities, that would be a presentation by itself. So what I am planning to do today is just concentrate a little bit more on inductor selection and just show you this fantastic aspect that RedExpert helps you with in terms of power losses. So before I start going into that, I'll just show you on here the general information provided in the table. So you have got the series name, the size, the inductance value, the rated current, the saturation current, the resonant frequency. I mentioned all of these before, length, width, and height in terms of dimensions, operating temperature, shielded or unshielded, as well as material. So you've got the data sheet as well. If you wanted to click into that to see the data sheet, you've got more than enough parameters to filter on to select an inductance value, a set saturation value range, an inductance value, a rated current, size, and so on and so forth. But this is not what we're here for. We're here to show you how we can use this in an example. And I'm just going to use I'll use a buck because we started talking about the buck. So in the buck on the side here, we have got what's called a design tool. So on the side here, this is called the design tool. We've got various different power topologies that you can use. And these topologies include the buck synchronous and non-synchronous, boost synchronous and non-synchronous, as well as SEPIC. We've got this magical extra icon down at the bottom in case you do not want to use any of these topologies. What if you're using a filter inductor just as an LC filter, or you're using one different type of topology, an LLCR, or a different two switch forward, and you need a calculation for losses? you can use this icon here to allow you to do that. But we'll start off with the simple, just to show you what this can do. And again, we are more than happy for you to contact the relevant sales individual, FAE in your local country area, and we're happy to take you through in a lot more detail on how you can fully utilize the power of RedExpert as a tool. But I'm just going to start off with a simple example. I've gone for a buck synchronous. So with a synchronous buck, naturally you have got the two switches here, and I'm going to go for a buck non-synchronous, and there is a reason for this, just to show you that with a buck non-synchronous, we do take into account the voltage drop across the diode when we calculate the duty cycle, and ultimately when we calculate the inductance value. So the equations that sit in the background here are determining the equations that are needed with parasitics in some occasions to calculate the required value of inductance. I'm going to put 0.7 as a more realistic value. I'm just going to keep these requirements here as they are, and I'm just going to say display results. The moment I say display results, I've gone down from 2,000 odd parts down to 177 parts that I can select from. And the way that RedExpert does this is it goes and does the calculation in the background, and based on your spec requirements, which we've entered in here, and comes up with an optimum inductance value, an average current, and a peak current based on that optimum inductance value. And then uses these as filters to filter for a suitable value of inductor that will do this job for me based on these specs. So that's what you see in terms of the filters up here. But again, one beautiful other thing that RedExpert does is it includes these extra 4 columns for you, which show you the AC loss, the DC loss, the total loss, as well as the temperature rise. So you are now no longer selecting a component blind in a way. Blind why? You've done the calculations, you've done your engineering job absolutely brilliantly, but there is a missing aspect which you can't see, which is how efficient is this inductor that I'm selecting. If I click into this column, just to show you, and by the way, non-applicable means this is a new series that hasn't had the testing done on it yet. That's why you do not see the AC, the total, and the delta T. You see just the DC, which is very simple, I squared RDC. We can tell that. But if I click into this column, just to show you, there is a part that has got 57.2 degrees temperature rise, and there is also a part that has got 8 degrees temperature rise. Now, which one would you select? Naturally, I would select the part that's a lower temperature, provided it's not the size of a brick. So I can see which is the size of a brick or not. 10.5. And what's this one? 6 millimeters. Okay, for an extra 4 millimeters, I'll definitely go for an 8 degrees temperature rise. Or I can go for something that's halfway house. The point here is, here's a 13 degree at 8 millimeters by 8. So the point here is it gives you this extra dimension, which from a design engineer's point of view, is a fantastic piece of information to allow you to maximize the efficiency of your design. I'm not going to finish here. I'm just going to spend a couple more minutes just showing you some other fantastic extra curves that we've included recently in RedExpert, which show you the variation of input voltage according to what you've mentioned here and how that impacts your power losses. So when we calculate the power loss for this inductor here, we calculate it at the worst case condition, which is for a buck at maximum input voltage. So you will see here 207 milliwatts. That's why you see 207 milliwatts here. And we will also split into DC and AC. So you see the components of power loss as part and parcel. We'll also show you what happens if you decide to change switching frequency. So we've said 500 kilohertz. If you go down, you're going to increase losses quite substantially in that particular inductor. If you go up, you could drop it down. Now, playing with frequency, I said, is your degree of freedom before. But naturally, we also have to take into consideration losses in the transistor switch as well, so, and the diode. So that's also part and parcel of the overall. And we show you as well the impact on load onto the overall losses as well. So if you change your load beyond 2 amps or below 2 amps, how that impacts things as well. So it gives you a very comprehensive way of looking through even variations in your design and how the selection of this particular inductance works for that, and whether it is the right part or not, without you having to keep going back and change these requirements. You can see some of these variations down here. One last aspect, ripple current, 40% is a default value that we have used as a default for the calculation of the ripple, what we see as the optimum ripple for a power inductor. So go. So I think I will leave you with these examples here. I've included a slide at the back end. I'm sure you're familiar with our website, and there's a contact link down at the bottom, just allows you to select the company you need and the country you're in. It'll give you the details of that. If you need to contact any sales individual or FAE in that country, please help yourself. The details are available there. Thank you very much for your attention, and happy to take your questions.
So thank you for your good presentation. It was really interesting. Now we would like to turn our attention to your questions and wait a little while until some questions have come in. Just take a look. Okay, I think here's the first question. What ripple factor should be used?
That's a good question. So that I mentioned, that was one of the last things I mentioned. So the ripple factor set in RedExpert at 40%, there is a set of equations that can be calculated that indicate at 40% you get the most efficient balance between the amount of energy stored plus versus the amount of ripple, I guess, reduction that you're going to get. So there is a knee point versus various different duty cycles of operations, I should say, that indicates 40%. But what I don't want people to think about, and you will see this, by the way, if you decide to play with the examples I put in, you do not have to follow 40%. Sometimes you put 60% or 100% and you end up with a more suitable inductor for your design. So 40% is not a holy grail or an absolute requirement. It is, again, your degree of freedom. So sometimes increasing the ripple factor may, in other words, reducing your inductance value, can have a lot of impact on improving efficiency, if anything. So it's all about balancing DC and AC losses overall, and temperature rise, size of the part naturally, inductance value. So all of this you can do very simply and easily within RedExpert by changing that number. Thank you for the question.
Thank you for answering. So the next one.
I've got a question here. Yeah. Why do I need an inductance in a step-down converter? The reason or the need for an inductance or an inductor in the output of DC-DC in general, step-down or buck regulator, is to filter the switched input. So the way that the buck works is you have got a series MOSFET element. That series element switches on and off. So what you're doing basically is chopping the input voltage. And as you're chopping that input voltage, you're looking at a method of averaging that chopped voltage in order to get a nice, clean, constant output voltage. That's what a regulator is there to do. So to do so, you put in an LC filter, basically, and that's what that LC filter is doing. It's taking that ripple in voltage now, that switched on and off voltage, and smoothing it down into a nice, constant output voltage. Hope that answers the question.
Sounds good. So maybe we can go to the next one.
Print? Yep. I've got. Oh God, they're coming. They're coming thick and fast. Here we go. Can I store and print my RedExpert simulation data. You can save it using a shared link, or you can share it using a shared link, but sometimes the shared link does expire. So what I would suggest is you can save it as a CSV file. There is a possibility of you downloading this into Excel for reporting purposes. We've had this with various different customers requesting to include some of this information as part of their selection and reporting of design documentation and reporting. So that's a possibility. Yes, absolutely. Are you agree with that the best source, McLiman? I'm not sure what the, I mean,
I think there's
for
a second
inductor
one
and
here.
transformer.
Yes.
Okay, okay. I'm not familiar with McLiman in terms of, I'm assuming that that is a book or a publication of some sort. So I wouldn't be able to give you my opinion, Ismail, I'm sorry. So, but from a sort of an inductor and transformer, if you're talking about designing components from scratch, that would involve quite a substantial task, because it's not just about selecting core material, it's also about selecting the type of wire, the mechanical arrangement to ensure stability. So yes, okay. So I think from that point of view, the idea behind doing this as an off-the-shelf solution is to simplify this process. I have had to, in the past, design inductors, transformers from scratch because I couldn't use commercial off the shelf in the aerospace industry. So that being the case, we had to select the core and the wire. And I'm telling you, this is not simple. It takes a lot of time and effort and to try to realize a product in that sense. And at the end of the day, you're still also subject to a big question mark about the losses that I've mentioned today, until, of course, you go into the lab and start testing the part itself. But the idea behind RedExpert and today is that you don't have to go in the lab. You can trust the information that you get on this and the information coming from RedExpert to allow you to down select to a suitable part that will do the job for you before you've gone in to identify the losses that you're getting.
Okay, thank you very much. I think we have to finish now the presentation, but if there are any questions left, we will answer them via email afterwards. So thank you very much for your attention, and I hope you enjoyed our presentation. The next presentation topic is capacitors. Wish it was so simple. Ideal versus real and its impact on signal integrity, noise, and EMI performance. So see you there, enjoy our digital days, and goodbye.